Hey there, time travel enthusiasts. Today we're diving into the mind-bending topic of time travel. Get ready, because we're exploring all the possible ways time travel could happen in simple terms. Time travel, a concept that has captured the imagination of humanity for centuries. To understand time travel, we must first explore the theoretical methods proposed by physicists and cosmologists. Method 1. Theory of relativity. The theory of relativity, proposed by Albert Einstein in the early 20th century, fundamentally changed our understanding of space, time, and gravity. There are two main branches of the theory: special relativity and general relativity. Here's a brief explanation of both, along with some examples. Special relativity. Special relativity deals with the relationship between space and time in the absence of gravity. One of the key principles of special relativity is that the laws of physics are the same for all observers in uniform motion. This means that the fundamental laws of physics don't change regardless of how fast you're moving. One of the most famous consequences of special relativity is time dilation. This means that time appears to pass more slowly for objects that are moving relative to an observer. For example, imagine you're watching a spaceship travel close to the speed of light. From your perspective, time inside the spaceship would appear to be passing more slowly compared to time on Earth. This effect has been confirmed experimentally with high-speed particles. The Halfwell-Keating experiment, conducted in 1971, was a fascinating demonstration of the effects of time dilation as predicted by Einstein's theory of relativity. Joseph C. Halfwell and Richard E. Keating, physicists at the United States Naval Observatory, conducted this experiment by using atomic clocks aboard commercial airliners. In this experiment, the atomic clocks aboard commercial airliners were flown in opposite directions around the world. The eastward traveling clock gained time compared to the stationary clock by about 59 nanoseconds, while the westward traveling clock lost about 273 nanoseconds. These tiny but measurable differences confirmed Einstein's predictions of time dilation due to both velocity and gravitational effects, providing empirical evidence for the theory of relativity. Now, let's understand general relativity. General relativity extends the principles of special relativity to include gravity. According to general relativity, gravity is not a force in the traditional sense, but rather a curvature of spacetime caused by mass and energy. Imagine spacetime as a flat sheet of paper. Massive objects like stars and planets curve the fabric of spacetime around them, and this curvature influences the motion of other objects. One of the most famous predictions of general relativity is gravitational time dilation. Clocks closer to massive objects like Earth tick more slowly than clocks farther away. For example, clocks on satellites orbiting Earth actually run slightly faster than clocks on the surface because they're farther from the massive body of Earth. General relativity also predicts gravitational lensing, where the path of light is bent by the gravitational field of massive objects. This effect has been observed during astronomical events, such as when light from distant galaxies is bent by the gravity of closer objects like clusters of galaxies. These are just a few examples of how the theory of relativity has been confirmed through experiments and observations, and how it has revolutionized our understanding of the universe. Method 2. Wormholes. The concept of wormholes was first introduced by physicists Albert Einstein and Nathan Rosen in 1935. Imagine folding a piece of paper so two distant points touch each other. That's what a wormhole does in space-time. Step through one end, and you could pop out in a different time, just like a movie. There are two main types of wormholes: traversable and non-traversable. Traversable wormholes would theoretically allow for safe passage from one end to the other, while non-traversable wormholes would either collapse too quickly or be too small for anything to pass through. While wormholes are mathematically consistent with the laws of physics, there is currently no experimental evidence to confirm their existence. Additionally, even if wormholes do exist, creating and stabilizing them would require technologies and understanding far beyond our current capabilities. Thus, while wormholes are a fascinating concept in theoretical physics and science fiction, their practical realization remains purely speculative. Method 3. Black holes. Einstein discovered that gravity from massive objects caused time to slow down. Therefore, while black holes will simply crush anything that enters them, by staying outside of its event horizon, you could travel years into the future relative to an observer beyond its gravitational field, while for you just a few days would have elapsed. Method 4. Looking back in time. FTL travel could also present us with the intriguing theoretical possibility of traveling 4 light hours away from Earth, turning around, and watching the light from Earth 4 hours ago arrive. We would essentially be watching 4 hours of history from Earth being replayed as its light arrived. Even now, There's nothing to preclude us looking back through time to observe events from long ago. Every time you gaze out at the stars, you're looking at history. You're looking at things that occurred thousands or hundreds of thousands of years ago. With a good telescope, you can watch things that happened millions of years ago. If you just want to look into the past 4.24 years, you can look at the closest star, after the Sun, to the planet Earth. Method 5. Quantum time travel. Quantum mechanics describes the behavior of particles at the smallest scales. Some interpretations of quantum mechanics suggest that particles can exist in multiple states simultaneously and may interact with their past or future selves. While quantum mechanics is a well-established theory, the idea of using it for time travel is highly speculative and controversial within the scientific community. Practical implementation would require a deep understanding of quantum phenomena and technologies far beyond our current capabilities. Well, there's a paradox called the grandfather paradox. Imagine you build a time machine and travel back in time to a point before your grandfather met your grandmother. While in the past, you accidentally murdered them, thus altering the course of history and preventing your own birth. If you were never born, how could you have traveled back in time in the first place to prevent your grandparents from meeting? This paradox poses a fundamental challenge to the concept of time travel because it suggests that altering events in the past could lead to paradoxes and contradictions. In this case, it's called the grandfather paradox because it involves the hypothetical scenario of killing one's own grandfather, thus creating a contradiction in the timeline. The grandfather paradox raises profound questions about causality and the nature of time. If time travel were possible, would changes made in the past alter the present and future? Or would the timeline somehow correct itself to avoid paradoxes? Could there be multiple timelines or parallel universes to accommodate different outcomes resulting from time travel? Share your thoughts in the comments below. And there you have it, folks. 6 captivating pathways through the mysteries of time. Which one resonates with your imagination the most? Share your thoughts in the comments below. Don't forget to like, subscribe, and hit that bell to stay tuned for more journeys into the unknown. Until our next voyage, may your dreams be filled with the echoes of history, the colors of the present, and the whispers of the future. Farewell for now. Thanks for watching.